Greetings, everyone. In our review of the independent samples t-test, we established that the t-test is used to compare two means. There are two variables involved, one independent variable and one dependent variable. The independent variable is categorical with two values, and the dependent variable is quantitative. The independent variable separates the sample into two groups, and the means of the dependent variable for these groups are compared. When the scenario becomes more complex, specifically when the independent variable has more than two values, the independent samples t-test can no longer be used. You might argue, yes, I can conduct multiple t-tests. If there are three means, I could compare mean 1 with mean 2 with mean 3, and mean 3 with mean 1. The problem with running multiple t-tests, however, is that the type 1 error rate becomes severely inflated. This is where the one-way ANOVA provides the best approach for comparing three or more means. The term ANOVA stands for Analysis of Variance. Similar to the independent samples t-test, one-way ANOVA involves two variables. The dependent variable is quantitative, while the independent variable is qualitative with k values, where k is 3 or more. The k levels of the independent variable divide the sample into k groups. Remember that each group is drawn independently from its underlying population. The goal of ANOVA is to test whether the k population means the average values of the dependent variable of the k groups differ from each other. To run an ANOVA, we follow the same 5 steps of hypothesis testing. Step 1 is to state the hypothesis. The null hypothesis states that all k population means are equal. The alternative hypothesis, also called the research hypothesis, states that at least one pair of means is not equal. Keep in mind that as long as there is one pair of means that differs significantly, we reject the null hypothesis. Step 2 is to choose the level of significance. Usually, alpha equals 0.05 is used unless there are specific reasons to choose a different value. Step 3 is to calculate the test statistic. In ANOVA, the test statistic is the F ratio, not a t-test. Step 4 is to make a decision. Compare the observed F value with the critical value, or when using SPSS, comparing the p-value associated with the observed F value against the alpha level. This determines whether to reject or fail to reject the null hypothesis. Step 5 is to interpret the results, report the conclusion, and provide an answer to the research question. Let's use an example to go through the steps. Suppose a consumer advocacy group wants to compare the performance of 3 car models. Random samples of 5 owners are selected from each model, and each owner reports how many times their car required major repairs in the past 5 years. In this example, can you tell what the dependent and independent variables are? The dependent variable is the number of major repairs. The independent variable is the car model, which has 3 categories, so k equals 3. The null hypothesis is mu1 equals mu2 equals mu3. meaning that the average number of repairs is equal across all three car models. The alternative hypothesis says that the mean of group I does not equal the mean of group J for some I and J, where I and J can have any values of 1, 2, or 3 as long as they're not the same. This seems complicated, but all it's saying is that at least one pair of car models differ significantly in the average number of repairs. We will use alpha 0.05 given the small sample size. In a separate video, I showed you steps 3 to 5, including how to run one-way ANOVA in SPSS and how to make a decision and reach a conclusion based on the output. In this video, I would like to highlight a few additional things about one-way ANOVA. First, it's critical to state hypotheses clearly and specifically. For example, if the independent variable has 4 categories, you're comparing 4 means. The null hypothesis should be written as all 4 means are equal. Do not write it in a generic format like mu1 equals mu2 equals mu3 all the way to mu(k). For the alternative hypothesis, a common mistake is to say mu1 not equal to mu2 not equal to mu3 not equal to mu4. This implies that none of the means are equal. Why is this wrong? Because the null and alternative hypotheses together need to cover all possible outcomes. The null hypothesis says all means are equal. If the alternative hypothesis says none of the means are equal, what has been left out? The possibility that some means might be equal while others differ. Remember, as long as there is one pair of means showing a significant difference, we need to reject the null hypothesis. Therefore, the correct alternative hypothesis is simply that not all means are equal. Stating the hypotheses correctly is important because not only do they set the direction for the test, but they also help you with the conclusion once you make a decision to either reject or fail to reject the null hypothesis. Next, I would like to explain the rationale of the ANOVA test. This part is not required, but it helps your understanding of the procedure. Unlike the t-test, ANOVA uses an F-test. The F-test is based on the principle that there are 2 ways to estimate population variance. If the null hypothesis is true, both variance estimates are unbiased and should be similar in value. In order to get the 2 different ways of estimating population variance, the total variation in the dependent variable is partitioned into within group variation, which is random variation among individuals in the same group, and the between group variation, which is variation among group means. The sum of squares is computed and divided by the respective degrees of freedom to obtain mean squares, which are variance estimates. I do not require you to learn the mathematical details of the calculation because SPSS can do the work in a few clicks. But if you're interested, I have provided a file in the weekly Canvas module that shows the calculations step by step. As a quick outline here, if the null hypothesis is true, the within group and between group mean squares should be similar. So their ratio, the F statistic, should be close to 1. If group means differ, the between group mean square becomes much larger and the F statistic increases. Without going into the details, This is how you understand what is going on. Let's assume that the null hypothesis were true. The 15 cars drawn from the 3 underlying populations were indeed from the same population, because all means are equal and all populations have equal variances. Treating them as samples from the same population, they are used to estimate the within-group mean square because their variations are due to random differences within a population. From a different perspective, if the null hypothesis were true, the 3 group means could be treated as 3 random values from the same underlying population as well. Even though there are only 3 values, they can still be used to estimate the population variance, which is called the between-group mean square. The mean square values, as the 2 variance estimates of the underlying population, should be very close in value, and their ratio, calculated in the F statistic, is expected to be close to 1. However, if the groups truly have different means, the mean square estimated from the 3 group means would be biased and would have a much larger value than the within-group mean square. Therefore, the F-test values would be much larger too. When I said that the 3 underlying populations had equal variances, did you want to ask me why? The next topic will answer that question. ANOVA has 3 main assumptions. The first is independence, which means subjects are sampled independently. The probability of one being selected has nothing to do with the probability of the others being selected. The second is homogeneity variance, which means the underlying populations have equal variances on the dependent variable. This assumption is tested in SPSS when running ANOVA. Violations can be serious, especially with unequal sample sizes. The third is normality, which means the dependent variable is normally distributed in each population. Minor violations are generally not problematic, particularly with larger samples. As with any significance test, it's important to report effect size to show practical importance. There are different ways to measure effect size. In this course, we use eta squared as a measure of effect size in ANOVA. Eta squared is calculated as the between-group sum of squares divided by the total sum of squares. As a quantification of the strength of association between the independent and dependent variables, it represents the percentage of variance in the dependent variable explained by the independent variable. In the car model example, if the between-group sum of squares is 40 and the total sum of squares is 64, eta squared equals 0.625. This means that about 62.5% of the variance in the number of major repairs is explained by differences in car models. Be cautious that the term effect size does not imply causality. When interpreting results and reporting findings, you need to avoid words that imply causal relationships. Finally, let's compare ANOVA with the t-test. When there are only 2 groups, meaning that the independent variable has 2 values, you can run either a t-test or a one-way ANOVA. The t-test is usually preferred because the result is easier to interpret and it allows testing of directional hypotheses. ANOVA cannot test directional hypotheses. For instance, if you want to know if one car model is better than another, that is a directional hypothesis. which requires a t-test. If the hypothesis is non-directional, meaning simply testing whether the means differ, both tests produce the same p-value. In fact, the observed f-value is the square of the observed t-value, and the same relationship holds for the critical values as long as the same alpha level is used.